Hey guys, so for today's topic, we're going to discuss stoichiometry, which is defined as a calculation of the quantities of chemical elements or compounds involved in chemical reactions. So there are many different types of chemical reactions in chemistry. To name a few, there are combustion, addition, substitution reactions, synthesis, and decomposition reactions. But for the sake of simplicity, all of these reactions can be better expressed as equations, where the chemical species interacting are written out as variables, which are in turn multiplied by coefficients denoting the quantity of the chemical species participating in your reaction. So to expand a little bit further on this, the chemical species that interact in your reaction are defined as formula units. So your formula unit can be an ion, it can be an atom, it can be a molecule, and it can exist in any physical state. So liquid, gas, plasma, solid, it does not make a difference so long as it participates in your reaction. Those formula units are going to be weighted by coefficients, which don't need to be, but are preferably whole number multiples indicating the quantity of a chemical species participating in your reaction. Lastly, you have your reaction arrow, which indicates whether a reaction is reversible or irreversible. Since the arrow in this particular reaction is going from left to right, we know that the species on the left-hand side are reacting to produce products on the right. So a chemical equation for a reaction is considered balanced when you identify coefficients for each of your formula units such that the number of atoms belonging to each of the elements in your reaction are the same on both the left and the right hand sides. So we'll elaborate on this further in the next slide. So there are some important conditions that you need to consider when you are balancing your equation or performing stoichiometry. The first of which, like I said earlier, is to make sure that the number of atoms corresponding to each element are the same on the left and right hand sides of your equation. This can be defined as your mass balance. Um, so take, for example, the combustion of methane to produce carbon dioxide and water. If you take a look at the individual elements participating in your reaction, you see you have one carbon on both the reactant and product side, four hydrogens, and four oxygens. So in addition to adhering to the principle of mass conservation, chemical equations also have to adhere to the principle of charge conservation, such that the net charge on the left and right hand sides of your equation are equal. Take, for example, the oxidation of solid copper by silver ions to produce copper ions in solid silver. When undergoing reactions, some atoms will actually become ions with elevated oxidation states. So, the oxidation states on those ions have to be offset by the charge of your other reactants such that the net change in charge as you go from reactants to products is zero. If you take a look at the left-hand side of this equation, you have a net charge of plus 2, basically 2 silver ions. It gives rise to a single copper ion with an oxidation state of plus 2. So as you can see, the uh, charge balance in this equation has been maintained. So now that we've discussed the structure of chemical equations and how to balance chemical equations using the application of stoichiometry, let's go through a couple of examples, beginning with the combustion of methane into carbon dioxide and water. So if we take a look at this chemical equation, one of the first things we notice is that the carbon and hydrogen atoms that exist in a single species on the left-hand side of the reaction are actually independent of each other on the right-hand side of the reaction, which basically means that we can independently adjust the number of carbon and hydrogen atoms without affecting the number of instances of the other. What's better still is that carbon and hydrogen in our products are only linked to oxygen, which exists as a lone diatomic species in our reactant stream. So what we can do here is modify the number of carbon and hydrogen atoms in our products so that they equal the number of atoms in our initial species of methane. And then we can adjust the coefficient on our diatomic oxygen to account for whatever discrepancy we create. So we have three carbons on the left-hand side of our equation, which means we should also have three carbons on the right-hand side. I'm going to multiply this species by 3. We have 8 hydrogen atoms on the left-hand side of our equation, and we have 2 on the right. So we can account for that discrepancy by multiplying our water molecule by 4. So now we have 3 carbons on the left and right-hand side of the equation, 8 hydrogen atoms on the left and right-hand side of the equation. Now the only discrepancy we have left is an oxygen. On the left-hand side of the equation, we have 2. On the right-hand side of the equation, we have 10. So we can easily account for that by giving oxygen a coefficient of 5. Now let me just clean up this mess that we've made. So if we were to do a mass balance on the left and right hand sides of our equations, we would say carbon, hydrogen, oxygen. We have 3 carbons, we have 8 hydrogens, we have 10 oxygens. Look at the right-hand side of our equation. We have, again, 3 carbons, we have 8 hydrogens, and we have 3 times 2, 6, and 4 times 1, 4, 10 oxygens. So this equation has been properly balanced. So now that we've properly balanced our first reaction, let's move on to the second, which features the fermentation of sugar into alcohol and CO2. So one of the first things that we notice when we look at this equation is that the hydrogen present in our reactant is only present in one of our two products. So that combined with the fact that hydrogen has the most atoms attributed to it is going to motivate us to try and balance for hydrogen first. So one of the first things we should do when we attempt to balance this equation is just write out the mass balance on the reactant and product sides. So, if you take a look at your reactants, you'll notice that you have 6 carbons, 12 hydrogens, and 6 oxygens. Whereas on the product side, you have 3 carbons, 6 oxygens, or 3 carbons, 6 hydrogens, and 3 oxygens. So if we're going to try and balance for hydrogen atoms first, we could start by multiplying our ethylene alcohol by a coefficient of 2, which would change the number of carbon atoms on our product side to 5. It would increase the number of hydrogen atoms to 12, and it would increase the number of oxygen atoms to 4. So, the number of hydrogen atoms on either side of the equation are now balanced. But we still had to put in some more work to balance the number of carbon and oxygen atoms. How can we do that? Well, if we multiply our CO2 by a coefficient of 2, now we wind up having 4 plus 2, so 6 carbons, and then we also wind up with 2 oxygens plus 4 oxygens, which gives you 6 oxygens. So by multiplying our ethylene alcohol by a coefficient of 2, and our carbon dioxide by a coefficient of 2, we were able to balance the numbers of atoms belonging to each element on either side of our equation. So this example has not been properly balanced. So moving on to our third example, we have the synthesis of hydrazine, N2H4, and ammonium chloride, NH4Cl, from ammonia and chloride. So similar to our last problem, we can start this example by performing atom balances on the reagent and product sides of our reaction. And if you take a look, you'll see that on the reactant side, we initially have one nitrogen atom, three hydrogens, and two chloride atoms. On the right-hand side of the reaction, we have three nitrogens, eight hydrogens, and one chloride atom. So based on what I said in the last example, you might be tempted to start our stoichiometric analysis by finding a mass balance for hydrogen. The only problem is that at the outset of this example, there really is no whole number integer that we can use to balance the number of hydrogen atoms in our reactant and product streams. So it might be a better idea for us to look for a different element to balance. And my personal preference would be chloride, just because it exists as a lone diatomic molecule on the reagent side, reagent side of our reaction. So, um, if we wanted to balance the number of chloride atoms on the left and right hand sides of this reaction, uh, we could easily just multiply our ammonium chloride by a factor of 2. Um, Here is how it would change the atom balance in our product stream. So our initial goal was to balance the number of chloride atoms, which we've done. We now have two chlorides in our product, two in our reactants. We now have 12 hydrogen atoms and four nitrogens on our product side as well. Um, And unlike the initial conditions for our equation, we now do have a situation where we can balance the number of hydrogen atoms on the left and right hand side of the equation through the use of a single whole number integer. And that integer would be 4. So if we multiply the ammonia on the reactant side of our equation by a coefficient of 4, then we wind up having 12 hydrogen atoms, 4 nitrogen atoms, and 2 chloride atoms um, in our reactant stream, which balances the equation. So our last example is photosynthesis, in which water and carbon dioxide come together to give us glucose and diatomic oxygen. So we are going to go about this example the same way we went about the others. Uh, so we begin by writing out mass balances for the reactant and product sides of our equation. On the reactant side, we have one carbon, two hydrogens, three oxygens. On our product side, we begin with six carbons, 12 hydrogens, and eight oxygens. So going from what we discussed in previous examples, our first course of action is going to be to attempt to balance the element that has the most atoms attached to it. So that would be hydrogen with 12 atoms on the product side. So if we want to balance the number of hydrogens on the reactant and product sides of our equation, we are going to have to multiply our water molecule by 6, such that we wind up with 12 hydrogen atoms on the left-hand side of our equation. So in addition to changing the number of hydrogen atoms, we're also going to go from having 3 oxygens to 8. So just like that, we have balanced two of the three elements taking part in this reaction. And the nice thing is that for our carbon balance, the carbon dioxide can be modified and only impact the number of diatomic oxygen molecules on the right-hand side of our equation. So the reason why this is nice is because we can multiply CO2 to give us our carbon balance, and then we can multiply our diatomic oxygen by whatever coefficient we need to compensate for the subsequent deficiency in oxygen atoms. So if we multiply CO2 by a coefficient of 6, then we'll go from having one carbon atom on the left-hand side of our equation to 6. And rather than having 8 oxygen atoms, we are going to wind up having 18. So the subsequent deficiency of oxygen atoms can be rectified by multiplying our diatomic oxygen on the right-hand side of the equation by 6, in which case the number of oxygen atoms on the right-hand side of the equation goes from 8 to 18 as well. So this equation is now balanced. So in conclusion, stoichiometry is defined as the calculation of the quantities of chemical species that participate in a reaction. Chemical reactions themselves can be modeled as equations. The chemical species participating in the reaction are expressed as formula units, which are weighted by coefficients. The coefficients, of course, will let you know how many instances of each formula unit participate in the reaction, and reaction arrows, which indicate reversibility. So stoichiometry is performed as a means of achieving a state of mass and charge balance by determining the right coefficients for each formula unit. So stay tuned for the next video where we plan on combining what we've learned on dimensional analysis and stoichiometry. Have a nice one.